This video is mostly just concerned with how to import data and then how to store individual columns. So on the second page, where if you want to import the physics graduate school data, I'm going to call it physics just like I did on that page. The function you need is read.csv since it's a CSV file. If your first argument is file.choose with open parentheses like that, then after I finish typing out this command, I'm going to get a pop-up window, which is much simpler than trying to recreate whatever the directory is. So now if I press enter, there's the pop-up window. And I wanted physics graduate school, then open, and it's in there. The thing I wanted to point out was that you don't get any sort of acknowledgement from R that it's there. If you want to check, if you type physics, since that's what I called it before, then enter, it shows up. So it's in there. The one thing that you would probably want to do, however, is you would probably want to save at least one column by itself as a vector. That's the next thing, where there are two ways that you can do it. One way is that you could use the header, since the header does have terminology there, school and stipend and so forth, or you could just use the column number. I would personally use the column number. So let's say if you wanted stipend, then I guess you have to be kind of careful. So if I'm just going to call it stipend like that, all lowercase, the thing you have to be careful of is that the header is case sensitive. So the $ specifies a column heading, and if I don't capitalize stipend, this won't actually work. There's no acknowledgement of that, but watch if I type in stipend now, there's nothing there. But if I go back up, so if you use the up arrow, you can cycle through your previous commands, and then if I change this to a capital S and then print it, it's in there. So if you're going to use the column headings, you have to be careful about that. You have to watch out for case sensitivity. What I would personally do is I would do it like this instead. So it's in the thing that we called physics, and it's in the second column because school is in the first. So the comma 2 says, give me the second column. And now if I print it, it's in there. So either way will work. And I usually use the numbers, but some people like to make it more descriptive and use the column headings. So if you want to do that, you can do that too. Then the next thing would be, once you have your data imported, you would want to probably do some kind of hypothesis test. So if it's for a mean, it would be t.test. And your first argument should be your data. So if I wanted to do one about the stipend, that's what it would be. And let's say I wanted to look for evidence that the average physics graduate school stipend is more than $20,000. So then my null would be mu equals 20,000. And then my alternative would include a greater than, which you specify like that. So the alternative would have either greater, less, or two dot-sided in quotes, depending on if you have a greater than, less than, or not equal to in the alternative hypothesis. This does have output, and it looks like we are getting a p-value that's just a little bit too big to reject the null if you're using this conventional significance level of 0.05. Other than that, to kind of run through the rest of this document, the next thing that really comes up is proportion tests. Those are pretty straightforward. So a proportion test for a single sample, like on page 5, where if you have your sample proportion, you just put that in as the first two arguments with the numerator and then the denominator. So for that first one where it's 55 over 90 for the sample proportion, you put in the 55 first, then the 90. Then you're testing a null of p equals 0.7. So there's your null. That goes in next. With an alternative with a less than as the inequality, so alternative equals less. And then you can put in the correct equals f if you want to. That turns off Yates's continuity correction, and it makes what you get in R closer to what you would get if you used a normal distribution, because R actually uses a chi-squared. That's why up here there's an x squared. That's what that's referring to. You don't actually need to use that. The only thing that's going to matter for us is the p-value, which is farther along in that line, that 0.03287. That's the thing that we actually want. And that's really all that you would need to get out of the output. There is other stuff that's in here, like down here you get a confidence interval. This confidence interval looks weird because if you specify a one-sided alternative, R will compute a one-sided confidence interval, which is a thing that we never talked about. The thing that we talked about as being a confidence interval is actually a two-sided confidence interval. Let's see, other than that, page 6 has a built-in data set. There are a ton of those. If you Google it, you can see what they are, but there are a ton of built-in data sets in R, and I just needed one that would have a few different variables where one was quantitative, so that was why I used that warp breaks one. But what you would do ultimately would be maybe a little bit more like the example with the taxis that starts on page 7. So we can run through that one. First you have to import the data, and I called it taxis there. I can do the same thing. I'll call it taxis, and there's my arrow, which would really be called the assignment operator in the sense of you're assigning the data to be called that term. And then file.choose, so that way we'll get the pop-up window, and there is a header, so header equals T, or true. Then we want the taxis. And then in the taxis CSV, if you look at it, fare is in the second column. So once again, just like earlier in the video, we want 2 in the column. So I'm going to call this fare, and then it would be taxis 2, and then t.test with fare, mu equals 15, and alternative equals greater, if you want to see if there's evidence that the average fare in Chicago is more than $15. And we're getting a p-value that's really tiny, so it looks like there's a lot of evidence supporting that idea that the mean fare is greater than $15. On page 8, where there's a proportion test for a difference of proportions, the only real difference there compared to a single proportion test is that you have to use the combine function in order to combine the two numerators and two denominators together. So your first argument ends up being like that, where it's C with the 48 and the 103. That's basically you telling R that here are my two numerators, the 48 and the 103. Then your next argument, you have to use the combiner again for the two denominators, which are 97 and 227. So there you're telling R, those are my two denominators, 97 and 227, in the same order that the numerators are in. I guess that's true. You got to keep the order consistent there. Then the alternative is a greater than, so we got to get that in there. And then once again, the Yates continuity correction. If you leave the Yates continuity correction off, I'm not going to care on the extra credit assignment. Enter, you get the output, and then there's the p-value right there, 0.2485. So it looks like here you would not reject the null. On the last page, page 9, there's a difference of means with independent samples hypothesis test using R. So with that one, it's the Scottsbluff and Torrington CSV file. So again, with read.csv is the function that you're going to use with file.choose to avoid having to type out the directory, and then header equals true, and then there's that. And if you look at the file, Scottsbluff is first and Torrington is second, so column 1, column 2. So you want a comma 1 inside the brackets for Scottsbluff, comma 2 inside the brackets for Torrington. So if SC stands for Scottsbluff, then it's going to be sc.tor column 1, and then tor is Torrington, that's going to be sc.tor column 2, like that. And just like before, when you use the read.csv function, or if you store individual columns as vectors, there's no acknowledgement that that's happening. If you want to see it, you can. If I print SC, there are the Scottsbluff numbers. If I print tor, there are the Torrington numbers. The NAs aren't a problem for using t.test. If you wanted to do something like get the sample mean for Scottsbluff, you'd have to take them out using the na.omit function, but we don't need that here. And then if we're going to do the t-test, so t.test with Scottsbluff, Torrington, then it's a two-sided alternative on that page. So alternative equals 2.sided, like that. And then there's the output with a giant p-value. Oh, watch this. You could also not specify the alternative if it's a two-sided alternative, because that's the default. If all I do is this, the t.test, and I have my two vectors, I get the exact same thing. Look at the p-value right there. Look at the p-value right there. Same test. So you can get away with that with a two-sided alternative if you want to. You're going to get what you're supposed to. So I guess you really only have to specify the one-sided alternatives. But that's basically it. If those things make sense, then you should be able to blow through that second extra credit assignment.